Hi, Monica, and today I'll be presenting Group 2 Statistics Project on Chapter 2 Probability. Alright, so let's get started with a little bit of history. The Nuova Chronica, which is the first ever recorded probability book, was found in the 14th century by a History of Florence by the Florentine banker and official Giovanni Villani, which includes much statistical information on population, ordinances, commerce, trade, education, and religious facilities, and has been described as the first introduction of statistics as a positive element in history, though it is important to know that neither the term nor the concept of statistics as a specific field yet existed. Mathematical methods of statistics emerged from the probability theory, which can be dated to the correspondence of Pierre de Fermat and Blaise Pascal in 1654. Christian Huygens in 1657 gave the earliest known scientific treatment of the subject. Jacob Bernoulli's Ars Conjectandi, the posthumous of 1713, and Abraham de Moivre's Doctrine of Chances in 1718 treated the subject as a branch of mathematics. In the modern era, the work of Kolmogorov has been instrumental in formulating the fundamental model of probability theory, which is used throughout statistics. Although statistics requires basic math skills, it is not categorized as mathematics. Alright, so now let's start with a little bit of definition so that we can be on the same page. An experiment is an act or process of observation that leads to a single outcome that cannot be predicted with certainty. There are two probability rules, and those are that all sample probability must lie between 0 and 1. It is important to know that probability is often expressed in a decimal or a percentage, which leads to the second rule, in which the sum of the probabilities must be 1. An event is a specific collection of a sample point, and a sample point or sample space is the most basic outcome of an experiment, and sample space is the collection of all of its sample points. All possible outcomes are called sample space. For example, when flipping a coin, we have two sample points. Can either be heads or tails. But when tossing two coins, we can either get a head first and another head, or we can also get a head and then a tail. If we keep going down the sample space, we will find that we can also get tails, heads, or tail, tail. Here's a table showing the probability of tossing a coin, where one could get 3 heads, no tails, shown on the right, and when we can get 2 heads, 1 tail, 2 heads, 1 tail. We can also get 1 head, 2 tails, picking on the right, or all tails. These tables are often very useful because they give an illustration of really what the probabilities would look like. Sample spaces and probability. We are asked to write the sample space for the given experiment, in which a dollar coin and a 50-cent coin are tossed. When 2 coins are tossed, we can either get heads or tails, tails or heads, 2 tails, or 2 heads. This would be our answer, the sample space. All the possible outcomes in order. It is important to remember that although we can have heads and tails, tails or heads, the order of the outcome does matter. In our second example, a card is selected from a deck, and we're asked to find the probability of finding an ace. Out of a deck of 52 cards, 4 of them are an ace. Simplified, we have 1 over 13, which gives us a probability of 7.69%. In example number 3, we have a bag containing 5 pennies, 4 nickels, and 6 quarters. If a coin is chosen at random, what would be the probability of choosing a penny? Total, 5 plus 4 plus 6. Total of 15 coins in the bag. Now we're asked about the probability of pennies. Since there are only 5 pennies in the bag, we'll put 5 out of 15. Simplified form would be 1 out of 3, 1/3, which is 33%. On our next example, we're asked to consider a family of 4 baby crocodiles. We have to find the probability of 3 males and 1 female. First of all, we start by writing the sample space. This problem, the order of the outcome does not really matter, since what we're really looking for is that no matter the order, we will find 3 males and 1 female. We find that out of 5 possible outcomes, only 1 of them matches the description of 3 male, 1 female. Therefore, the probability of having 3 males and 1 female is 20%. On our next example, 2 dice are rolled, and we're asked to consider the probability that the sum of the dice will be 4. Then again, we start by writing all of the possible outcomes of rolling 2 dice. 36 outcomes total. And then we look for the one that matches our description, which would be the sum of the dice is 4. We find that only 3 out of the 36 possible outcomes match the description. 3 over 36, which is further simplified into 1 over 12, which is 8.33%. Mutually exclusive events and the addition rule. Mutually exclusive events are 2 events that are mutually exclusive or disjoint. This is a key word. If it is possible for them to occur together. Formally, 2 events, A and B, are mutually exclusive if and only if A is disjoint from B, and that is equal to 0. On our first example, determine whether the following pair of events is mutually exclusive. A card is drawn from a deck. The probability of F, if it is a queen, probability of G, it's a diamond. Are these mutually exclusive? The answer is no. The event is not mutually exclusive because one can draw a card of Queen of Diamonds, which means that both events can occur at the same time. On our next example, we have the addition rule. A fair dice is rolled, and the events H and I are as follows. H, the probability that an odd number will show. I, probability that an even number will show. The probability of, first of all, we start by writing the sample space, the probability of H. Odd numbers in the dice, 1, 3, and 5. 3 out of 6 gives us a 50% chance. The probability of drawing an even number, 2, 4, and 6. Then again, 3 over 6 gives us a 50%. This event is mutually exclusive because both events cannot occur at the same time. See, compared to the other example that we had, we can have a queen and a diamond. But in our next example, we cannot have a number that is odd and even at the same time. That's the difference between our mutually exclusive. On our next example, we have a table showing individuals classified by either being Persian, American, male, or female. A total of 100 individuals. Example number 1 asks us for the probability of a male given that they're Persian out of a total of 100 men. We have 39 male Persians for a total of 39%. Probability of the individual being a female given that she's American. American, female. I'll have 5 over 100. Example number 3 asks for the probability of a male given that he is Persian. Have a 95 over 100, giving us a total of 95%. The probability of a male or a female is 0.5. Moving on to independent. One must understand that an event can either be mutually independent or independent. It cannot be both at the same time. The distribution of the number of folklore and children's books checked out of a city's main library and at a smaller branch on a given day is as follows. Here we have a chart showing the main library and the branch. Folklore books, children books, out of a total of 550 books. The probability of getting a children's book, 150. The total children's over overall total, 550. For a 0.27, which is a 27%. The probability of getting a book from a branch, given that it's a children's book, is 0.33%. Then we're asked, is the fact that a person checks out a folklore book independent of the main library? The answer is yes, because you can find a folklore book in the main library as well. We have the conditional formula, which consists of the probability of A given B is equal to the probability of A intersect B over the probability of B. This is the formula you'll be using to solve this problem, in which we have hillbillies and surfers divided by male and female for a total of 100 subjects. The probability of hillbillies is the hillbilly over the total, which is 43, it's found right over here, divided by the total amount of subjects. It's the sample size, divided by the whole population. Example number 2 asks us for the probability of hillbillies given that they're males. So we have 43, total number of hillbillies, over the total number of males. See, the number in the bottom will always be the total. 43 over 91 gives us a total of 47%. Example number 3 asks us for the probability of male given that they're hillbillies. See, we have a 39 over the total 43 hillbillies, giving us a percentage of 91. Finally, we have the probability of surfers given that they're female, having a total of 5 over the overall total of 9, with an outcome of 55.6%. In this new formula that we'll be learning, we have the probability of K, which is success in N trials. N over K times the probability to the K, raised to the K power, Q to the power of N minus K, giving us N over K is equal to N factorial over K factorial times N minus K factorial. N representing the total number of trials, K representing the number of success. N minus K is equal to the number of failures. Lowercase p is the probability of success in one trial. It is important to notice that this is a lowercase p. Uppercase P stands for the total probability. Q stands for 1 minus P, which is the probability of failure in one trial. Example problems. A coin is tossed 10 times. What is the probability of getting 6 heads and 4 tails? And again, we try to identify our N, our K, N minus K, P, and Q. Alrighty. So the total number of trials is 10, since the coin is tossed 10 times. The number of success is 6, since we're trying to get 6 heads. N minus K will be the number of failures, so we'll let the number of tails represent that. The probability of success in one trial is 0.5. One coin has 2 sides. 1 over 2 is equal to 0.5. And again, Q, which is equal 1 minus P, which we already found. 1 minus 0.5 is equal to 0.5. And here we go. P. Then again, we find the formula for P. P of the K success in N trials is equal to N over K, P raised to the power of K, and Q raised to the power of N minus K. Now, if we were to find this previous problem, plug it into a calculator, into the formula, we'd find N CR times 0.5 raised to the power of 6, and again, success raised to the power of success is the power of failure raised to the power of failing. That will give us a probability of 4 success in 6 trials. NCR is done with a calculator command, which can be found by pressing math and then PRB and then number 3, which is NCR, after you press the first number, which would be your N for the equation. So 210.5 raised to the 6, 0.5 raised to the 4, for an equal of 20.5%. Example problem. Basketball player has 80% chance of sinking a basket on a free throw. What is the probability that he will sink only 3 baskets in 5 free throws? Okay? So our total number of trials will be 5. See? 5 free throws, and that he will only make 3 out of those 5. So success. And then the remaining 2 would be the failure. Probability of success is 0.80, 80%. And then the remaining would be the probability of failure, which is a 20%. NCR is equal to 5, total number of trials, C, by the total number of success. 10 times 0.8 raised to the power of 3, 0.2 raised to the power of 2, gives us a total of 0.2048, which we later simplify to 20.48%. A telemarketing executive has determined that for a particular product, 20% of the people contacted will purchase the product. If 10 people are contacted, what is the probability that at most 2 will buy the product? N is equal to 10. Total number of trials. K, total number of success, will be 2. At least 20%, correct? Or that 20% of the people. 2. And minus K, 8. The remaining. The probability is that 20% of them will actually call back or actually buy the product. And the probability of failure is 1 minus P, which is 0.8. And again, NCR is equal to number of total trials over the number of success. So we want 2 out of 10 people to buy the product. That's pretty much what we're looking for. Okay? 45.2 over raised to the power of 2 and 0.8 raised to the power of 8 gives a total of 0.302, which is later simplified to 30.2%. Expected value example problems. This problem, you're about to make an investment which gives you a 30% chance to make $60,000 and a 70% chance to lose $30,000. Question is, should you invest? So 30% chance to make $60,000, which is $18,000. 60,000 times 0.30. But then there's a 70% chance to lose $30,000. Again, 30,000 times 0.7 gives us 21,000. For a total of negative 3,000 of the expected value. you would be losing more than what you would be gaining out of this investment. Therefore, do not invest because there's a negative expected value. A game involves drawing a single card from a standard deck. One receives 60 cents for an ace, 30 cents for a king, and 5 cents for a red card that is neither an ace or a king. If the cost of each draw is 10 cents, the question is, should one play the game? There is a 4 out of 52 probability that you will draw a card that's an ace. A 4 out of 52, same as the ace, that this card will be a king. And there is a 22 out of 52 chance that this card will be a red card, but that it will not be an ace or a king. See, here's 60 cents for an ace, 30 cents for a king, 5 cents for a red card. It's neither an ace or a king. Multiply these together, get 4.62 cents. Multiply this together, 2.31. Multiply this together, 2.12. The expected value is 9.05 cents, which is less than the 10 cents it costs to play the game. So you will be losing money. Cost you 10 cents, you would only be making 9.05. Why would you want to do that? So just don't play. During his 4 years at college, James received A's in 30% of his courses, B's in 60% of his courses, and C's in the remaining 10%. If A is equal to 4, B is equal to 3, and C is equal to 2, what would be her GPA? Okay, considering A, again, is equal to 4, B is equal to 3, and C is equal to 2. 4s, 3s, and 2s have a 30% chance. 30% of her courses were A's. It's 4 times 0.3, so a total of 1.20. 3 times 460, so a total of 180. And 2 times 0.1 gives a total of 0.20. When we add all of these together, we have a total of 3.2 GPA. That's it for today, folks, on Chapter 2, Probability. Thank you very much for listening.